Hello students, good evening. So in the last class, I gave introduction about chemical kinetics. Let us recap whatever we have discussed in the earlier class. In the last class, to begin with, I discussed about the introduction part of chemical kinetics. We discussed about the scope of chemical kinetics. We discussed about the rate of reaction, the factors affecting the rate, and rate constant. So these are the concepts which we have discussed in our earlier class. In today's class, let us study about the order of reaction, which is very important. If you understand what is order of reaction, if you understand this concept, you can solve most of the questions which comes for your competitive examination. So students, be attentive in today's class. Let us discuss about the order of reaction. So today's discussion will be about order of reaction. Students, let us consider a reaction in which a reactant A is converting into product P. Let us write the rate equation for this. We know that rate of a chemical reaction is directly proportional to the concentration of reactant A. Let X be the concentration of reactant A. So the concentration term which is present in the equation should be raised to an appropriate power. So reactant A concentration, I have taken it as X. So I have raised it to the power, appropriate power. So let us write the equation. Rate will be equal to remove this proportionality sign, I introduce a constant K. So K into A to the power of X. And we know that K is a rate constant. Here X is nothing but the order of reaction. So the order of reaction is taken as N, which will be equal to X. I have taken an example of a reaction involving only one reactant molecule. Now I take one more example. Let us consider another reaction in which a reactant A reacts with another reactant molecule B to give product P. Let X be the concentration of concentration with respect to the reactant A. Let Y be the concentration with respect to reactant B. Now let us write the rate expression for this. Rate is directly proportional to the concentration of reactant A, which is raised to the power of X, and concentration of reactant B, which is raised to the power of Y. Or we can write the rate equation. Rate will be equal to K into concentration of reactant A, which is raised to the power X, and concentration of B, which is raised to the power Y. Now I write the order for this reaction. For this particular reaction, order is, I take it as N, order of reaction, I take it as N, where N is X plus Y. So with the help of these two equations, now let us define what is order of reaction. Order of reaction with respect to a particular reactant A. Here only one reactant molecule is involved in the equation. Order of reaction with respect to reactant A is the power to which the concentration term is raised. So the concentration term X is raised to the power. Order of reaction with respect to a particular reactant is the power to which the concentration term is raised. Whereas if I take a reaction involving two different reactant molecules, then order of the reaction can be defined as it is the sum of the power of concentration term which is raised in a rate equation. Here order of the reaction involving two reactants A and B is X plus Y, which is the sum of power of concentration of A and B. Now, let us see how the reactions are classified based on the order. Based on the order, the reactions, the chemical reactions are conveniently classified into following types. Now, I am going to write on the board which are the types of order which we are going to study in today's class. So, based on the order, the reactions are conveniently classified into following types. Number 1, it is first order reaction. Then second order reaction. Students, RXN is nothing but reaction, the short form which I am writing. So, the third one is again third order reaction. Then zero order reaction. Fractional order reaction. And the last is pseudo first order reaction. Pseudo first order reaction. Okay. Just now I told you what is order of reaction. We know that order of a reaction with respect to a reactant is the power to which its concentration term is raised. Whereas if two reactant molecules are involved in the equation, then order is the sum of the powers of concentration term which is raised in an experimentally determined equation, which we call it as a rate equation. And this is how the chemical reactions are classified based on the order. Now let us discuss one by one. What is first order reaction? What are the examples? Let us see how we can understand the order of reaction by chemical equation. First, I am going to discuss about first order reaction. I take few examples to make you understand what is order of reaction. Understanding the definition is different. Understanding the concept in detail is very different here. So, order of reaction, let us see what is its significance in a chemical reaction. If I take first order reaction, I take example decomposition of phosphorus pentachloride. Phosphorus pentachloride decomposes to give phosphorus trichloride and chlorine. One more example I take, hydrogen peroxide. Hydrogen peroxide decomposes to give water and oxygen. So, to balance the equation, I am going to add stoichiometric coefficient 2. Here also, I am going to add 2. Now, the equation is balanced. I take one more example, decomposition of nitrogen pentoxide. Nitrogen pentoxide decomposes to give nitrogen dioxide and oxygen. Again, to balance the equation, I am going to add stoichiometric coefficient 2. So that here I should add 4NO2. So, 2 to the 4 atoms of nitrogen is present in the left hand side, 4 nitrogen, 2 5 the 10 atoms of oxygen, 4 to the 8, 8 plus 2, 10. I take one more example, thionyl chloride, SOCl2. Thio means sulfur, thionyl chloride, SOCl2 decomposes to give, SO2Cl2 decomposes to give SO2 plus Cl2. Again, this is an example for first order reaction. Now, let us study what is this first order reaction. I take one example here. I take particular hydrogen peroxide to make you understand what is first order reaction. Let us write the rate equation for this particular reaction, hydrogen peroxide. So, hydrogen peroxide, if I want to write the rate equation, we know that rate of a reaction is directly proportional to the concentration of reactant. The reactant here is hydrogen peroxide. Or I can write here the stoichiometric coefficient is 2 here. You can see that stoichiometric coefficient 2 to balance the equation which I have used. I can write the equation as rate will be equal to K into concentration of hydrogen peroxide. See, law of mass action states that the rate of the reaction is directly proportional to the concentration of reactant, where the reactants, where the stoichiometric coefficients are raised to an appropriate power. If I write 2 here, then I am following the law of mass action. Law of mass action based on the stoichiometric coefficients which are prescribed as per the balanced chemical equation. But here I am not going to write the stoichiometric coefficient 2 here. Let us see what is the difference here, and I call this equation as rate equation now. Now you will come to know what is the difference between the law of mass action and the rate equation very clearly. Now, according to this equation, if I increase the concentration of hydrogen peroxide by 1 time, if I write 1 arrow, think that I am increasing the concentration of the reactant by 1 unit, 1 time. If I increase the concentration of hydrogen peroxide by 1 time, the rate increases by 1 time. If I increase the concentration of hydrogen peroxide by 1 more time, the rate simultaneously increases by 1 more time. With increase in the concentration of hydrogen peroxide by 1 time, the rate increases by 1 time. Hence, the order of the reaction with respect to hydrogen peroxide, I take it as 1. You can see that the stoichiometric coefficient is 2. If I want to write the equation by following the law of mass action, I should raise the concentration of reactant to the power 2. But here I am getting 1. So, where I write the order of reaction is 1. Order of reaction tells us how many times the rate of the reaction increases with increase in the concentration of reactant. Whether the rate increases by 1 time, whether the rate increases by twice, whether the rate increases by thrice. Order of the reaction significance is, it will tells us how many times the rate increases with increase in the concentration of the reactant. Students, in this particular equation, we can see that when we increase the concentration of hydrogen peroxide by 1 time, the rate is increasing by 1 time. If I increase the concentration of hydrogen peroxide by one more time, the rate is simultaneously increasing by one more time, hence the order is 1. To make you understand this concept better, I will take the help of graph. Students, let us assume that we are plotting a graph by taking a rate along y-axis and concentration of hydrogen peroxide along x-axis. Now, let us divide the scale, let us write the scales here. From year to year, let us take it as 1 unit year. Now, when the concentration of hydrogen peroxide is increased by 1 time, you can see that the rate is increasing by 1 more time. When I increase the from year to year, you can see when the concentration of hydrogen peroxide is increased by 1 time, the rate is increasing by 1 time. If I increase the concentration of hydrogen peroxide by 1 more unit, the rate increases by 1 more unit. So, with increase in the concentration of hydrogen peroxide every time by 1 unit, the rate is increasing by 1 unit. Hence, I say that order of the reaction is 1. So, a first order reaction is the one whose order is 1, a simple definition. So, order of the reaction, when I gave the definition I say that order of the reaction is the sum of the powers of concentration terms, which is raised in rate equation. See, that is the definition, but understanding the concept is very important here. You can crack many questions which appear in your competitive examination if you understand this concept better. So, whatever the examples which I have taken, all these are examples for first order reaction. The decomposition of hydrogen peroxide, nitrogen pentoxide, phosphorus pentachloride, all these are example for first order reaction. Now, students, it is clear that when we are writing the law of mass action, the chemical equation by following the law of mass action, here concentration of hydrogen peroxide is there, here 2 is the stoichiometric coefficient which has to be raised to the power here. Whereas, when I following the rate equation here and when I am determining the order of reaction, see here I have taken it as 1. Because when the concentration of hydrogen peroxide is increased by 1 time, the rate is increasing by 1 time. So, the rate equation is, that is the reason why we call it as experimentally determined equation. Rate equation does not depend on the stoichiometric coefficients. Sometimes it may matches with the stoichiometric coefficients, but not always. I take one more example to make you understand this. I take example of phosphorus pentachloride. Students, I hope you are understanding this very important concept. Be attentive. I take one more example here, that is phosphorus pentachloride. Let us write the equation here. So, rate of the reaction directly I am writing will be equal to K into concentration of PCl5, phosphorus pentachloride. Students, When I increase the concentration of phosphorus pentachloride by 1 unit, the rate increases by 1 unit. Hence, the order with respect to the phosphorus pentachloride is 1. So, the order I take it as n, denoted by n, so I write it as 1. Here, you can see the equation is balanced here. Here, if nothing is there, we know that the stoichiometric coefficient is 1. For this particular equation, we can see that the order of the reaction is balancing with the, matching with the stoichiometric coefficient. But in case of hydrogen peroxide, the stoichiometric coefficient is 2, the order is 1. So, order, stoichiometric coefficients, they are not related to each other. In some reaction, the order matches with the stoichiometric coefficient, but not always. I hope you have understood the order of reaction, the first order reaction. Students, you should remember the examples, and you know that order is an experimentally determined value. We should carry out the experiments to understand, and we need to observe how the rate increases. It's not a theoretical concept. By looking at the chemical equation, we can't say which order is that. It is an experimentally determined value. So, order of the reaction is determined by carrying out experiment. Now, let's go to the next order, that is second order reaction. Yes, second order reaction. I take two examples for this. Chemical combination of hydrogen and iodine to give hydrogen iodide. Students, this is an example for second order reaction. I take one more example. I take an ester, an organic reaction, an organic molecule. I take ester, methyl acetate. Ester, when it is made to react with sodium hydroxide solution, we are going to get sodium acetate, CH3COONA, sodium acetate, and methanol, CH3OH. And this is also an example for second order reaction. Now, let us see what is second order reaction. I take example the first one, formation of hydrogen iodide. Here, let us write the rate expression. Rate will be equal to K into concentration of hydrogen and concentration of iodine, because hydrogen and iodine are the two reactant molecules which are combining to give hydrogen iodide. Now, let us study whether this is a first order second order reaction or not. When we increase the concentration of hydrogen by 1 unit, the rate increases by 1 unit. Hence, the order of the reaction with respect to hydrogen is 1. When I increase the concentration of hydrogen by 1 more unit, again the rate increases by 1 more unit. Hence, the order of the reaction with respect to hydrogen is 1. With increase in the concentration of hydrogen by 1 unit, the rate increases by 1 unit. Hence, order with respect to hydrogen is 1. If I take iodine, with increase in the concentration of iodine by 1 unit, the rate increases by again 1 unit. With increase in the concentration of iodine by 1 unit, the rate increases by 1 unit. Hence, the order with respect to the iodine is also 1. When you increase the concentration of iodine by 1 more unit, the rate increases by 1 more unit. Hence, the order with respect to iodine is 1. Now, I want to write the overall order of reaction N. So, we know that according to the definition I said, the overall order of reaction is the sum of the powers of concentration term. The sum of the powers of concentration term which is raised in rate equation. So, sum of the powers of concentration term which is raised in rate equation, that is 1 plus 1, which will be equal to 2. You can see that. So, this is an example for second order reaction. So, be attentive. It is very confusing concept. You should be attentive to understand this. So, I am using many other supporting tasks to make you understand this particular concept better. So, listen carefully. When the concentration of hydrogen is increased by 1 unit, the rate increases by 1 unit. 1 arrow stands for 1 unit. If I increase the concentration of hydrogen by 1 more time, the rate increases by 1 more time. Hence, I am saying that order with respect to hydrogen is 1. If I increase the concentration of iodine by 1 unit, again the rate is increasing by 1 unit. Hence, the order with respect to iodine is also 1. If I want to write the overall reaction, it is 1 plus 1, which will be equal to 2. It is a second order reaction. So, the formation of hydrogen iodide is a second order reaction. Hence, how do we define second order reaction? The reaction in which the sum of the powers of concentration term is 2. That is what we call it as second order reaction. Again, I take an example. I take help of graph again to make you understand this particular concept. Very, very important. Be attentive. Now, I take graph here by taking rate along y-axis and concentration of hydrogen along x-axis. Hydrogen is one of the reactant molecule. Now, these are the scale along x-axis and this is the rate scale along y-axis. If I increase the concentration of hydrogen by 1 unit, the rate increases by 1 unit. So, I am going to get a line like this, from year to year, the rate increases by 1 unit. If I increase the concentration of hydrogen by 1 more time or 1 unit, the rate increases by 1 more unit here. So, hence the order of the reaction with respect to hydrogen is 1. Then, I take with respect to iodine, again I will plot a graph by taking iodine. So, rate and concentration of iodine. When I increase the concentration of iodine by 1 unit, the rate increases by 1 unit, hence the order with respect to iodine is 1. Now, I am going to join this. If I increase the concentration of iodine by 1 more unit, the rate increases by 1 more unit, hence the order with respect to iodine is 1. Overall order of reaction is 2. So, this is how we need to understand the concept. Students, order of the reaction tells us how many times the rate increases with increase in the concentration of reactant. I repeat this statement, how many times the rate increases with increase in the concentration of reactant. Whether it is increased by 1 time or it is to increase by twice or thrice. That is the significance of order of reaction. Now, let us go to the next third order reaction. So, before discussing third order reaction, students, it is the time to discuss about the context question. In the last class, the context question winner is Mr. Roger. He has successfully answered the right answer, that particular question which they have asked in the last class. Hence, he will get 1 autumn session free. All the best, Roger. And today's context question is, I am going to read out today's context question. Today's context question is, a catalyst. A catalyst, 4 options are there. A catalyst increases, first option, increases the heat of the reaction. A catalyst, first option is increases the heat of the reaction. Second one, decreases the heat of the reaction. Third one, does not alter the heat of reaction. Fourth one, increases the number of collision. Student, I repeat the question. A catalyst, number 1, option 1, increases the heat of reaction. Option 2, decreases the heat of the reaction. Option 3, does not alter the heat of reaction. Option 4, increases the number of collision. Think and answer about this question. Okay. And in the last class, I gave a question, CPP question, that is an example of autocatalysis reaction. Many of the students have not answered this particular question, that is an example of autocatalysis. First of all, what is autocatalysis? Let me discuss this question, then after that I will go for again the third order reaction. A reaction in which the reactant molecule itself acts as a catalyst. There is no need of adding a catalyst externally. Such reactions we call it as autocatalysis. Here the correct answer is decomposition of nitroglycerin. Students, nitroglycerin is also called as dynamite. It is an explosive. So, nitroglycerin, when it decomposes, it gives various oxides of nitrogen. The oxides of nitrogen which is liberated during the course of reaction will catalyze the reaction. Such reactions we call it as autocatalyzed reaction. There is no need of adding catalyst externally. You have seen many catalytic reaction. For example, potassium chlorate. You take potassium chlorate powder. Potassium chlorate powder on heating, it liberates oxygen gas, dioxygen. So the rate of the reaction is increased by adding manganese dioxide. Here manganese dioxide acts as a catalyst. But in the decomposition of nitroglycerin, there is no need to add the catalyst externally. Hence, it is auto-catalyzed reaction. The correct answer is the decomposition of nitroglycerin. Okay. I hope all of you are convinced about this particular question. Yes. Again, let's come back to the today's concept, that is order of reaction. Students, now let us take an example of third order reaction. Very important. I take example for this third order reaction. I take the chemical combination of nitrogen monoxide. Nitrogen monoxide reacts with oxygen to give nitrogen dioxide. Let us see whether the equation is balanced. So 2NO plus O2 to give 2NO2. So this is an example for third order reaction. I take one more example. Let us take ferric chloride. Ferric chloride reacts with stannous chloride to give ferrous chloride and stannic chloride. You can see that here the oxidation state of iron is +3, hence it is called as ferric. Here the oxidation state of tin is +2, it is called stannous. Here the oxidation state of iron is +2, again hence it is called as ferrous. Here the oxidation state of tin is +4, hence it is called as stannic. So this is the reaction which I have taken. To balance the equation, I am going to take 2 molecules of ferric chloride, again I am going to add 2 here. So 2 3s are 6, 6 plus 2 8, 2 2s are 4, yes, the equation is totally balanced. These two are example for third order reaction. Again, listen carefully, what is third order reaction? Let us write the rate equation for this, that is the formation of nitrogen dioxide. We know that rate is directly proportional to the concentration of reactants, that is nitrogen monoxide and oxygen. Or I take it as rate will be equal to K into concentration of nitrogen monoxide and concentration of oxygen. Students, listen carefully again, very important. When the concentration of nitrogen monoxide is increased by 1 unit, the rate increases by 2 times, 2 units. When the concentration of nitrogen monoxide is increased by 1 time, the rate doubles, the rate increases by 2 times. Hence, the order with respect to the nitrogen monoxide is 2. Similarly, when we study with respect to oxygen, when the concentration of oxygen is increased by 1 unit, the rate increases by 1 unit. When the concentration of oxygen is increased by 1 more unit, simultaneously the rate increases by 1 more unit. Hence, the order of the reaction with respect to the oxygen is 1. So, if I want to write the overall order of reaction, I should take it as the sum of the powers of concentration term which is raised in rate equation. Student, the equation, this equation we call it as rate equation, rate expression, rate law. All are one and the same. It is an experimentally determined equation. Why I am saying this experimentally determined equation? Because in this particular equation is arrived by carrying out an experiment. This particular equation will relates the rate of the reaction and the concentration of reactants. What happens to the rate of the reaction when the concentration of the reactants are increased or decreased? Hence, this is experimentally determined equation here. You can see that in this particular reaction, the order of the reaction is 3. With respect to nitrogen monoxide, the order is 2. You can see the stoichiometric coefficient is also 2. With respect to oxygen, the order of reaction is 1. The stoichiometric coefficient, nothing is there, it is to be considered as 1. As already I said that for some reactions, the order with respect to particular reactant matches with the stoichiometric coefficient. But stoichiometric coefficient and order, they are not related to each other. So this is an example for third order reaction. How we can define third order reaction? A reaction in which the sum of the powers of concentration term is equal to 3. The such reactions we call it as third order reaction. Okay, these two are the examples for third order reaction. Okay, next. I will go to the zero order reaction. First order, second order, third order with examples I am explaining here. Next is zero order reaction. Copy the examples. When I am writing the examples on the board, you need to copy it, and how I am relating that. That is also very important, students. Next is zero order reaction. I take few examples for this. Hydrogen combines with chlorine. This is I am discussing zero order. Hydrogen combines with chlorine in presence of sunlight to give hydrogen chloride. This is an example for zero order reaction. I take one more example, decomposition of ammonia. Ammonia decomposes in presence of platinum catalyst to give nitrogen and hydrogen in the ratio that is 1:3. So, these two are example for zero order reaction. Let me define what is zero order reaction. Zero order reaction is the one in which the rate does not depend on the concentration of the reactant. You increase the concentration of the reactant by whatever the times you want, the rate does not increases. There is no change in the rate of reaction. Such reactions we call it as zero order reaction. Here, the reaction between hydrogen and chlorine to give hydrogen chloride also takes place in dark, in absence of sunlight. But the reaction is very slow. The same reaction we are going to carry out in presence of sunlight. The reaction occurs at a very faster rate. Here, if I want to write the rate equation for this, rate will be equal to K into concentration of hydrogen and concentration of chlorine. Listen carefully, students, here. When the concentration of hydrogen is increased by 1 time, there is no change in the rate of reaction. Let us increase the concentration of hydrogen by 1 more time. There is no change in the rate of reaction. Here somebody is messaging how to increase the concentration. Students, it is an experimentally determined values. Order of the reaction is an experimentally determined value. I think it is Sudep. It is not an experimentally determined, it is not a theoretical concept. Here I am taking the examples of equations, but all this, whatever the concepts which I am teaching, it is an experimentally determined value. We need to carry out experiments in the laboratory. We need to take hydrogen and chlorine. Then we need to increase the concentration of hydrogen by keeping the concentration of chlorine constant. What do you mean by increasing the concentration? I have taken 1 mole of hydrogen to a reaction vessel. Again, I am going to add 1 mole to it. That means I am increasing the concentration of hydrogen. When I increase the concentration of hydrogen, initially I have taken 1 mole, again I am going to add 1 mole to that. But I find that there is no change in the rate of reaction. This is an experimentally determined value. You can't simply read the chemical equation and you can't predict the order of reaction. But you should know some examples of a chemical reaction, which order to it, which it is belongs to. Now, with respect to this, when the concentration of hydrogen is increased by 1 time, there is no change in the rate of reaction. When the concentration of hydrogen is increased by 1 more time, there is no change in the rate of reaction. So, the rate of the reaction does not depend on the concentration of hydrogen. You increase the concentration of hydrogen as many times you want. There is no change in the rate of reaction. Hence, the order of the reaction with respect to hydrogen is 0. When you increase the concentration of chlorine again here, by 1 time, by twice, by thrice, here 1 arrow for 1 time. So, when the concentration of chlorine is increased by how many times you want, there is no change in the rate of reaction. Hence, the order of the reaction with respect to chlorine is also 0. So, the overall order of reaction I take it as 0. Here, the rate of the reaction depends on what? The intensity of the sunlight here. If it is dark, the rate of the reaction proceeds at a very less slow rate. In presence of intense sunlight here, the rate of the reaction increases. The rate of the reaction does not depend on the concentration of the reactant here. Hence, I take this as an example for zero order reaction. Here also, in the decomposition of ammonia to give nitrogen and hydrogen. If you take this particular equation, that is decomposition of ammonia, let us write the rate equation for this. Rate will be equal to K into concentration of ammonia. When the concentration of ammonia is increased by 1 time, there is no change in the rate of reaction. When you increase the concentration of ammonia by 1 more time, again there is no change in the rate of reaction. You increase the concentration of ammonia by how many times you want, There is no change in the rate of reaction. Hence, the order of the reaction with respect to ammonia is 0. Why? The rate does not depend on the concentration of ammonia, students. Can you think? Think for a minute, few seconds. Why the rate of the reaction here does not depend on the concentration of ammonia? Why there is no change in the rate of reaction? The reason is, if you take platinum catalyst here, the reaction is taking place over the surface of platinum. Here, you are going to pass ammonia gas with a high pressure. When you pass ammonia gas, the ammonia gas gets adsorbed on the surface of the catalyst. When you pass ammonia gas, initially the ammonia gas molecules gets accumulated on the surface of the catalyst, nothing but it gets adsorbed on the surface of the catalyst. Further, when you pass ammonia gas, there is no change because already the surface area will be completely covered. When the surface area of the catalyst is completely covered, there is no space available on the surface of the catalyst for the adsorption of ammonia molecule. There is no change in the rate of the reaction. Here, the rate increases until the surface of the platinum is available. When the surface area of the platinum is completely covered, there is no change in the rate of the reaction. Hence, this is an example for zero order reaction. Okay, I hope you understood this. How do we define zero order reaction? The reaction in which the rate does not depend on the concentration of the reactants. That's all. Next, I take an example for fractional order reaction. Fractional order reaction. I take example, the reaction of hydrogen with bromine to give hydrogen bromide. This particular equation is an example for fractional order reaction. Let us see what is this. Let us write the rate equation. Rate is directly proportional to the concentration of hydrogen and bromine. Here I am going to write the equation directly. So, rate will be equal to K into concentration of hydrogen and concentration of bromine. When you increase the concentration of hydrogen by 1 unit, the rate increases by 1 unit. Hence, the order with respect to hydrogen is 1. If you increase the concentration of bromine by 1 unit, the rate does not increases completely by 1 unit. It increases by half the unit. Hence, the order of the reaction with respect to bromine is half. What is this half unit, sir? What is this 1 unit, sir? Again, I will take the help of a graph. Let us plot a graph by taking rate and concentration of hydrogen. This is for one reactant. Again, I take another example. Again, one more graph, rate and concentration of bromine. Let us divide the graph. Let us write the scale. These are 1 units here. Along x-axis, this is the concentration of bromine and this is the rate. 1 unit. From here to here, 1 unit. From here to here, 1 unit, like that. Again, let us write the same thing for this. Now, I take example for hydrogen. With respect to hydrogen, the order of the reaction I have written 1. When the concentration of hydrogen is increased by 1 time, the rate increases by 1 time. You can see that from here to here 1 unit, from here to here 1 unit. When the concentration of hydrogen is increased by 1 unit, the rate is increasing by 1 unit. Hence, the order of the reaction with respect to hydrogen is 1, I can write. You can see in the graph, from here to here 1 unit, from here to here 1 unit. When the concentration of hydrogen is increased by 1 unit, the rate is increased by 1 unit. When the concentration of hydrogen is increased by one more unit, the rate increases by 1 more unit, you can see. Hence, the order of the reaction with respect to hydrogen is 1. Whereas, if I take bromine, from here to here 1 unit here, let us take this as 0 as a reference. From here to here 1 unit. When the concentration of bromine is increased by 1 unit, what do you mean by 1 unit? I have taken 1 mole of bromine. I am going to add again 1 mole of bromine here. That is how we are going to increase the concentration in a reaction mixture. Now, when the concentration of bromine is increased by 1 unit, the rate does not increases completely by 1 unit. Maybe it increases by half the unit. If from 0 to from this point, if it is 1 unit, the rate increases by half the unit, half the time. Hence, the order with respect to bromine, I take it as half. If I want to write the overall order of reaction, I write it as 1 plus 1 by 2, which will be equal to 3 by 2. Hence, this is an example for fractional order reaction. How do you define fractional order reaction? It's the reaction in which the order of the order has a fractional value. And one more example I take for this, even the decomposition of carbonyl chloride, CO plus Cl2. Students, carbonyl chloride is also called as phosgene. It's a poisonous gas which is formed during the oxidation of chloroform. So, the decomposition of carbonyl chloride to give carbon monoxide and chlorine, this is also an example for a fractional order reaction. What is fractional order reaction? The reaction in which the order has fractional value, that's all. So, this is about fractional order reaction. Last but not least, I am going to explain about pseudo first order reaction. Very, very important. Pseudo first order reaction. Be attentive, students, very important. Pseudo first order reaction. I take example, sucrose. Sucrose on hydrolysis will gives glucose C6H12O6 and fructose C6H12O6. Glucose and fructose, they have same molecular formula. Glucose as an aldehydic group, fructose as a ketonic group. Glucose is called as a aldohexose, fructose is called ketohexose, they are sugars. Now, this is an example. The reaction is catalyzed by a mineral acid H+. Here, when you look into this reaction, particular reaction, if I write the rate equation, rate is directly proportional to the concentration of sucrose here. Sucrose is a cane sugar which is present in the sugar cane. So, concentration of sucrose C12H22O11 and concentration of water. Or I can write rate will be equal to K into concentration of sucrose C12H22O11 and concentration of water. Assume that here I have taken 100 ml of water. In that 100 ml of water, I have dissolved say around 10 grams of sucrose. And I added few drops of dilute hydrochloric acid. Now let us study the order of this reaction. If I increase the concentration of sucrose by 1 unit, I have taken 10 grams. I am going to add 1 more gram to that. I am increasing the concentration. When I increase the concentration of sucrose by 1 unit, the rate increases by 1 unit. Hence, I say that the order with respect to the sucrose is 1. Now I take water. I have taken just say around 100 ml of water. Now to this 100 ml of water, I am going to add another 1 ml of water extra. I am adding water to this. 1 ml of water is added to this reaction mixture which contains sucrose and water. When I added 1 ml, again when I increase the concentration of water by 1 unit, the rate increases by 1 unit. Hence, I say that the order of the reaction with respect to water is 1. This is how the one will expect about this particular equation. It seems that it is a second order reaction, 1 plus 1 will be, which will be equal to 2. But in actual practice, when we are preparing a sugar solution, always we take solute in a lesser amount, solvent in a greater amount. In this particular reaction, this is a second order reaction. The second order reaction can be converted into first order. How I am going to convert this into first order? Instead of to this 100 ml, again I am going to add 1000 ml of water. Instead of adding 1 ml or 2 ml like that, water I have taken, initially I have taken 100 ml, to that I am going to add 1 liter of water. When I compare the concentration of sucrose, the concentration of water is too large. So I have increased the concentration of water to a larger extent. If the concentration of water is increased to a larger extent, the rate does not now depends on the concentration of water. Assume that 100 ml I have taken, To that I have added 1000 ml. That is 1100 ml of water is present in this. Now if I add 1 ml to this, there is no change in the rate of reaction because practically the concentration of the water remains constant. Theoretically we are adding 1 ml extra, but practically it remains constant. It's like if we assume that in a beaker there is 100 ml of water, if I take 10 ml outside, there is decrease in the volume of water in a beaker. Assume that there is a pond. In that pond, by using motor pump, I am going to evacuate water. I use motor pump continuously for 5 hours and whatever the water that is present in the pond, I am going to take it out. So there is decrease in the volume of water in the pond. But if I do the same thing in a ocean, assume that in a ocean I am going to take out the water continuously using motor pump for 5 hours. Is there change in the concentration of water, volume of water? Theoretically, definitely, I am taking out. If I pump out water for 5 hours, say several gallons of water will comes out. But when I take the entire ocean it contains large volume of water. Practically, is there change in the water? There is no loss for ocean, even if we take water out. But in a small beaker, if I take 10 ml of water out, definitely. So when the volume is less, if we take out the reactant or if we add some volume of water, definitely there is effect in the change in the concentration. Practically it affects. But if I take large excess of water, there is no change in the rate of reaction, but because rate of the reaction does not depends on the concentration of that particular reactant which is taken in a large excess. Hence, the order of the reaction is 1 plus 0 here. Why 0? Because the concentration of water is taken in a large extent such that practically it remains constant. Theoretically, if I add 1 ml to this 1000 liter of water, definitely there is little bit change. Theoretically, I know that 1 ml of water is added, but practically it remains constant. Hence, the rate does not depend on that particular reactant which is taken in a larger proportion. Such reactions we call it as pseudo first order reaction. The meaning of pseudo is false. I define it now. A higher order reaction. This reaction is to seem to be higher order. The order is 2, I told, with respect to sucrose and with respect to water. A higher order reaction can be brought into first order. A higher order reaction, a second order reaction can be brought into first order. How? By increasing the concentration of one of the reactant to a large extent such that the rate does not depend on the concentration of that particular reactant, and such order we call it as pseudo first order reaction. The example which I have taken, it is inversion of cane sugar. Students, with this I conclude today's class. In today's class, I discussed about what is order of reaction, types of order of reaction with examples. Very, very important. Is it clear? So you should understand this. When you understand the order of reaction, the entire chemical kinetics becomes more easier for you. So in the next coming class, let us discuss about little bit about the factors on which the order of reaction depends. Is it clear? Okay then. So with respect to the concepts which I have discussed so far in today's class, students, I am giving 10 CPP questions. Answer these CPP questions. Think and answer. If you try to answer all these questions, definitely you will learn the subject effectively and you can score, you can answer all questions which appear in your competitive examination. Good luck, students.